Good morning. All right, so we are going to pick up where we left off yesterday, and I do apologize for the issue we had technology-wise yesterday. Hopefully, I've got those things resolved at this point. And if we do run into those same tech issues, I do think I have an alternative at least now, so hopefully that won't happen again. Get started though. Any questions, concerns, comments, anything like that anybody wants to address before we jump back into this section? All right, so let's go ahead and jump back in then. So you'll notice the slide I've got up right here. This is called the conjugate zeros theorem. So basically what this tells us is if we have a complex number, and remember by complex number, we're talking about those complex numbers that have the form a plus bi. So if that's one of our zeros of our polynomial, then its conjugate, which we called z bar, if you think back to section 1.6 that we did before, that z bar is the a minus bi. That's also going to have to be a zero. And the reason for this is when we solve these things and we use quadratic formula to get these imaginary roots, we're always going to have that plus or minus the square root piece. And so that's why we're always going to have a complex number and its conjugate whenever we're finding zeros. Okay, so just know if one of these is a zero, then its conjugate also has to be a zero. All right. Let's take a look at this one here. So we're given, in this case, that we're looking for a polynomial of degree 3, and we're given the zeros of 1/2 and 3 minus I. And we're asked to actually find what that polynomial would be. All right, so looking first at the zero of 1/2, what would one of my factors need to be to give us a zero of 1/2? Okay, Naomi? Sorry, yeah, so I'll pause and wait just a minute then. Okay, so Sarah says x minus 1/2, right? So that's one option. If we want to avoid fractions, right, just so that we're multiplying this thing out, we don't have to deal with all the fractions, is there another factor we could use that would still give us 1/2 as our zero without having to use any fractions there? So, and without using any decimals, right? Because 0.5 and 1/2, I agree, are the same thing, right? But if we didn't want to use any decimals or fractions. Okay, good, right? So in this case, I could, and I assume, Anthony, you meant 2x minus 1 in this case, right? So I'm going to write that. So if we were to use this as a factor, remember, if we set this equal to 0 now, we would add the 1, we would divide by the 2. That would still give us 1/2 as our 0, but now we're avoiding all those fractions. Okay, so if you use x minus 1/2, it's fine, right? You're going to get a polynomial that works. It's just that then you have to deal with the fractions when you're multiplying. So this is going to help us not have to do that. Now, what about the 3 minus I? What would be the factor that would give us 3 minus I as our 0? So I'll give you a hint. It's going to start with x. And so now how are we going to put this 3 minus I into this factor right here? What would that look like? Good, right? So remember, we have to change both of our signs this time. So this is going to give us x minus 3 plus I. So just anytime you've got a complex number like that, just make sure when you put it into your factor, both of these values are going to change sign. And so that's what we're going to get. Now, if we're looking for a polynomial of degree 3, how many factors do we actually need here? We need 3, right? Right now, we've only got 2. So now we've got to figure out, well, what's that third factor going to have to be? Well, think back to that last slide. If 3 minus I is one of our zeros, what else is going to have to be a 0 for this polynomial? Good. Its conjugate, 3 plus I, also has to be a 0. And so now we can write a third factor using this 0 right here. So what would that factor look like? Almost. There we go. Good. So it needs to be x minus 3 minus I. Because again, we want to make sure we change both of our signs here. So the 3 becomes a minus 3, the I becomes a minus I. And so that's going to be our third factor this time. Any questions just on the factors there? That's fine. Any questions there? All right, so now we need to multiply all this out. And like I told you before, I always look for the ones that have the i's and go ahead and multiply those first, because a lot of times a lot of the I stuff is going to cancel out. Then whatever we get for that, then we can multiply by the 2x minus 1. So I'm going to come over here. I'm going to do a box method for this one since we've got 3 terms in each. I need 3 terms across the top. I need 3 terms down the side. And so we're going to have x. We're going to have a minus 3. We're going to have an I. We have an x, a minus 3, and a minus I. All right, so now when we multiply, and I'm just going to go through these, x times x would give us x squared here. X times negative 3 is going to give us a negative 3x. X times I is xi. Negative 3 times x is negative 3x. Negative 3 times negative 3, positive 9. Negative 3 times I, negative 3i. Negative I times x is going to be a negative xi. Negative I times negative 3 becomes a positive 3i. And negative I times negative I is going to be negative I squared. Okay? So now, if we start looking at what we can combine here, right, we have our x squared. There are no other x squared terms here. So I'm just going to bring that down. Okay? Now, when we combine our x's this time, negative 3x and negative 3x, that's going to give us a negative 6x. Now, if we look, we have an xi and a negative xi. Those two terms right there are actually going to cancel each other out. So we know that's going to cancel. We also have this positive 3i and negative 3i. So those are going to cancel. And now I'm left with this positive 9 and this minus I squared. But what do we know I squared is equal to? Negative 1, right? I'm just going to change this right here to minus negative 1 instead. Again, anytime you see one of those I squares, just think that's negative 1. So this gives me a minus negative 1. So that's what I've got right here. Now, when I combine like terms, I have my x squared minus 6x. What are we going to get for 9 minus negative 1? Positive 10. Good. This just gives us a plus 10. Now I'm going to bring that back over here. We have our 2x minus 1. And then all of this multiplied together gave us this polynomial here. So x squared minus 6x plus 10. And now at that point, we still need to multiply these two polynomials together. And so it's up to you. If you want to do the box again, you can. I'm going to try to just distribute since I've got 2 and 3. So I've got 2x times x squared. That's going to give us 2x cubed. Then I'm going to do my 2x times my negative 6x. That's negative 12x squared. 2x times 10. It's going to be plus 20x. Negative 1 times x squared is negative x squared. Negative 1 times negative 6 plus 6x. And negative 1 times 10 is going to be minus 10. So let me pause there. See, are there any questions about how I got any of that now? All right, so now the last step, we're just going to combine like terms here. I don't have any other x cubed terms, so we keep our 2x cubed. I've got a negative 12x squared and a negative x squared here, so what should that give us? Good, so minus 13x squared. If I combine my x terms, what should we get? Good, positive 26x. And then nothing to combine the 10, so we have a minus 10 at the end there. So this right here is my polynomial that I'm looking for that would have these zeros of 1/2, 3 minus I, and 3 plus I. And we do indeed have a degree of 3 here. Okay, so always double check to make sure you have the correct degree. That's right, German. So if you have an imaginary value as one of your zeros, then its conjugate also has to be one of the zeros. Any other questions on that one? All right, anybody need more time to get that one down now? All right. All right, so linear and quadratic factors theorem. Okay, so what this theorem tells us is every polynomial that has real coefficients, and that's the only polynomials we're going to look at. We're never going to have imaginary coefficients or anything like that. They can be factored into the of linear and what we call irreducible quadratic factors, meaning quadratic factors that can't be factored any further. Okay, so anytime you're given a polynomial, as long as all the coefficients are real, we can always factor it down into linear and quadratic factors where those quadratic factors can't be factored anymore. So let's look at this. And so for this one, we're asked to factor it first into those linear and irreducible quadratic factors. And then we're going to factor completely, meaning we want to include any imaginary values that we would also get. Okay, so this is only going to include real values. This down here could include imaginary values. That's the difference. All right, so if we take a look at this one, if I'm trying to get this thing factored, right, and we start with x to the 4th plus 2x squared minus 8, any ideas on what we could do first here? Okay, we could do P's and Q's, right? So that's one option. In this case, though, if you look at this one, we've actually got a trinomial, right? So Kenneth, you're right. We can actually try to factor this thing, without actually having to look for P's and Q's. Okay, so always keep that in mind that that's an option, especially when you have a trinomial, right? Even though this is x to the fourth, because the middle term's an x squared, we might actually be able to just break this into two binomials and not have to go through that whole process of P's and Q's. Now, if this works, then we've got P's and Q's to fall back on, right? We can always go that route. But let's see if we can just factor this as is. So what would we need to give us x to the fourth? Okay, we're going to need an x squared in each set of parentheses, right? So x squared here, x squared over here. Now we can look down here at our 8, right? We need to get a negative 8. So what would be the factors that would give us a negative 8 this time? Good. So we want to use a 4 and a 2. And the reason that we're going to use 4 and 2 this time is because we still want to get this 2x squared in the middle. So now we just got to figure out the signs. So where are we going to put, in this case, we need a negative and a positive to get a negative 8, right? So where's the negative going to go and where's the positive going to go? Good. The 2 needs to be negative, which means the 4 is going to have to be positive this time. So now that would give us x to the fourth. We have a minus 2x squared plus 4x squared is going to give us 2x squared, and then positive 4 times negative 2 is negative 8. So that is factored now. Now, if we look at this, can we factor either one of these any further than that? Okay, so the x squared plus 4 cannot be factored, right? This is what we call a sum of squares, and remember that's never going to factor. We know we can't do anything with that. This one over here, technically not a difference of squares because 2 is not a perfect square, but you'll notice in the book what they're going to do is they're going to say, well, I can at least get real values out of that. So I'm going to set that equal to 0 to figure out what those other zeros would be, and then I'm going to use those as my limit factors. So if we were to solve this here, first step, we would move the 2 over. We'd have x squared equals 2. And so then what would I end up getting as my zeros for that part? Good. So we have x equals plus or minus the square root of 2, right? Because we're going to take the square root of both sides here. Just don't forget, we always need that plus or minus there. So now we have plus or minus square root of 2 as those two zeros. We said the x squared plus 4 does not factor, so that's an irreducible quadratic factor there. And then we can factor this thing right here technically into what two factors based off of these zeros? Good. So we're going to have x plus the square root of 2 times x minus the square root of 2. Remember, these are two zeros, positive square root of 2 and negative square root of 2. And so these would be the two factors that would come from those zeros. So this is now factored in terms of our linear and irreducible quadratics. These two factors linear because they're x to the first power, and this one right here being an irreducible quadratic because we can't factor that any further without using imaginary numbers. Any questions on that part? Okay. Now, if we look at the second part here, now we want to completely factor this, and we can include complex numbers this time. Right? So we know these two things aren't going to change, right? We're still going to have those two factors. But now we've got to think about what are going to be the factors that are going to come from this, and we're going to factor it down even further. Right? So how can we find the factors that are going to come from x squared plus 4, or the zeros that are going to come from x squared plus 4? set it equal to 0. Good. I'm going to take x squared plus 4. I'm going to set that equal to 0. So now my first step, move the 4 over. We're going to have x squared equals negative 4. And so this, when I take the square root, what am I going to get? Good. And don't forget, we still need plus or minus, right? So it's going to be plus or minus 2i, because the square root of 4 is 2. The square root of a negative value gives us the I, so plus or minus 2i. Now, if we want this completely factored, right, I'm going to come back up here. This x squared plus 4 then is going to factor into what two factors? Good. X plus 2i and x minus 2i. And then we already said we had the linear factors from up here, so we're just going to bring those down. So x plus the square root of 2 and x minus the square root of 2. So if you're asked to completely factor something, then we want to get it all the way down to linear factors where everything is an x to the first power, even if we have those imaginary numbers in there. If it just says linear and irreducible quadratics, we only want real values, so we would have to stop here if that's what we're asked for. Any questions on that one now? All right, anybody need more time on that slide? All right. Next section. Okay, so now we're going to look at rational functions. Okay, and so when you hear the word rational, what do we think? Good, fraction, right? So any function that can be written as a fraction, in this case, we're going to have x's in the numerator and denominator, or at least in the denominator. That's going to be the key. Okay, anytime we have that, then that's when we're going to have a rational function. This is a new section, yeah. So, sorry, I can tell you which section it is. It should be 0.6, rational functions. All right, so we're going to start out with the most basic of our rational functions. Okay, f of x equals 1 over x. We're going to look at the graph of that, and then we're going to talk about the domain and range. Okay, so go ahead and get the function first. And I'll actually go into Desmos, and we'll look at the graph together, and then we'll talk about domain and range there. Okay, so I'm going to share my Desmos graph. There we go. All right, so that's what our graph is going to look like for the function 1 over x. So if we're thinking about domain for this one, what does it look like the domain of that graph is going to be? Good, right? So if you look at the graph, right, it's going to go all the way to negative infinity because we're thinking about x values. So looking at the left-hand side of the graph, the left-hand side is going to negative infinity. We're going to have negative infinity. But then when we get to 0, notice the graph never touches 0, right? It goes down on the left-hand side and it goes up on the right-hand side, but it never actually touches the y-axis. So it never touches an x value of 0. So we have to make sure we stop our graph there. and then we're going to use a union, and then we're going to pick back up with 0, and notice the right-hand side of the graph is going to go all the way to positive infinity on the right-hand side, right? And so now, in this case, exactly what German's got there in the chat, negative infinity to 0. Just make sure there's a union between them, right? And then 0 to infinity, using parentheses here, right? Because we do not want to include the 0 value. Okay? So any questions on why that is the domain for that graph? Okay. And I'm sorry for all the background noise. All right, so now if we look at range, now we're looking at y values, right? Okay, so if we're looking at the values, what's going to be the smallest possible y value for that graph? Negative infinity, right? Because if you look right in the middle of the graph there, it curves down, and it's just going to go all the way down towards negative infinity in terms of the y values, right? So we know we start with negative infinity for our range. I promise I'm going to put the slide back up. I'm writing all this down, but I just want to make sure I leave the graph up so we can see it. So we're going to start from negative infinity. Then what happens? Where do we have to stop our range? What value is it never going to hit? 0, right? So if you notice the x-axis in this case, that's a y value of 0. On both sides, it's approaching, but it never quite gets there, right? So we have to make sure we're going from negative infinity to 0, not including the 0. And then the other piece of that, we're going to pick back up with 0, and we're going to go to what value? Infinity. Good, right? Because again, if you look right in the middle of the graph on the right-hand side this time, it's going up towards positive infinity in terms of the y values. So that second part of our range is going to be from 0 to infinity. So again, let me go back now and share my notes here. There we go. So you can see in this case, the domain, the x values go from negative infinity to 0, and then from 0 to infinity. Same thing for the range, from negative infinity at the bottom up to 0, and then from 0 to infinity all the way to the top. Any questions on that? Now, looking at the function itself, right? So 1 over x. Y is my domain from negative infinity to 0 and from 0 to infinity, where we are not including 0. There's a restriction, right? Specifically in this case, what are we looking at? Can't have a 0 denominator, right? So because we have that x in the denominator here, that can't be 0 because that would make this thing undefined, and that's why our domain is just this right here. So we technically could have just looked at the function, said, oh yeah, we know we can't have a 0 in the denominator, x can't be equal to 0, and we could have found the domain that way. Okay, but again, you're always going to have access to Desmos graphing calculator, right? So feel free to actually graph it and just make sure that that actually matches, what the graph shows us there. Any questions on that one now? All right. Now this might be a little difficult to read because I know some of the type is small. It is still in the slides though, if you just want to pull those up, or if you actually want to look at the digital version of the textbook. I'm basically going to be pointing to things on the graph though, so hopefully that'll be enough that you can kind of see what's going on. So if we look at this first graph right here, this vertical line is what we call a vertical asymptote. And the reason we call it a vertical asymptote is because our graph approaches that vertical line, but it never actually touches that vertical line. So if we think back to the graph that we just looked at, right, the 1 over x, we actually have a vertical asymptote at x equals 0 because on both sides of that graph, that curve is approaching that vertical line, but it never quite gets there, right? So you could have a situation where you're just approaching from the right-hand side. You could also have a situation where you're just approaching from the left. You could have a situation where, again, you're approaching from the right, but it's going down towards negative infinity, or same thing this way, as it's approaching, it's going towards negative infinity. And it could be on both sides, right? So it doesn't just have to be on one side. It could be more like the one we looked at before, where it's actually approaching on both sides. But in all of these cases here, we would call that vertical line a vertical asymptote. Now, the graphs at the bottom, these are all horizontal asymptotes because now we have a horizontal line that we're approaching, but we never touch, right? So our curve here is going to curve up. It's going to get close to that horizontal line, but it never actually touches it. Now, this one over here, right, this is important that we note, it could technically pass through the horizontal asymptote because it's more about what is it doing as we either get towards positive infinity or negative infinity. So as I go towards negative infinity now, this is still a horizontal asymptote because I'm never going to reach that horizontal line as I go towards negative infinity. Okay, so even if it passes through the line at some point along the curve, it's more about what is it doing to the left or what is it doing to the right. That's going to give us those horizontal asymptotes. Any questions on that? And again, it is more clear in the actual slides, right? So if you want to download those to be able to see that, all that information is there. And it's also in the digital version of the text if you want to look there too, okay? All right, so let's take a look at these now. So we're going to graph each of these functions, and we're going to state domain and range again. Okay, but this time we got a little bit more going on than we did before. All right, so let's start first function. So we got 2 over x minus 3. And again, I'm just going to put this in Desmos so we can look at it together. And I'll share that screen. All right, so this is our graph of r of x equals 2 over x minus 3. And so if we're looking in this case for the domain, so let's start there. I'm looking at my x values. What's the domain going to be for that graph? Good, right? So we're going to start from negative infinity. This time, we're going all the way up to positive 3, and that's the value that we can't have, right? Because we know if we put a 3 in the denominator there, that's going to give us 0 in the denominator. So we cannot include the 3. We're going to do a union. Again, pick up with the 3, and then we're going all the way to positive infinity. And so exactly what German has there in the chat, that's what our domain should be this time. Any questions on why that is the domain for that one? All right. What about the range for this one then? Good, right? So we're going to go from negative infinity to 0. Again, we need a union there, and then from 0 to infinity. So just like the range we had for the original function, 1 over x, right? It's going to look exactly the same because we still have that horizontal asymptote along the x-axis, right? So y cannot be equal to 0 this time. Any questions about the domain and range for that function? Okay. So let me show the other graph now. There's the 3x plus 5 over x plus 2. So again, we want the domain and the range. So what's the domain going to be for this one? Good, right? So we're going from negative infinity to negative 2, and a union, negative 2, positive infinity. Again, all parentheses there, right? Because we do not want to include the negative 2 for this one. And again, we can kind of look at the denominator and say, oh yeah, if we put a negative 2 in there, that's going to give us 0 in the denominator. That's why we end up with that vertical asymptote at negative 2 this time. All right, now, if we're looking for a range, what do you think the range would be this time? Good. So this time we're going from negative infinity to positive 3, union 3 to positive infinity. Again, all parentheses, because this time we have a horizontal asymptote at y equals 3. That's where the graph is never going to touch in terms of the y now. Any questions on that one? All right. So I'll just show you down here, just in case you didn't get it before. Domain for each of these, okay, that's what those should look like. Anybody need more time on that one now? Okay. All right, so let's look at this one now. All right, so if we're looking at that function, okay, we can look at the graph, right? So I'll put the graph up there. It might be a little bit more difficult this time to kind of pick out what the values are going to be. So we might actually need to do a little more digging into this one, okay, but just so you can see what the graph looks like. Let me go ahead and share that. All right, so there's our graph. So if we look at the graph, do you see either any horizontal or any vertical asymptotes? And where would those be if you do see them? Okay, so German says x equals 1 and y equals 2. All right, so you're saying we have a vertical asymptote at x equals 1 and then a horizontal asymptote at y equals 2, right? So those are both correct. So now, if we want to think about domain and range, then, if that's where our asymptotes are, what would be the domain for this function then? Good. So we're going to go from negative infinity to positive 1, and then union 1 to positive infinity. Again, all parentheses, because we do not want to include the 1 there. So that's good for the domain. Now let's talk about the range this time. Good. So this time the range is only going to go from 2 to positive infinity, because notice there's nothing on our graph that's below that horizontal line, right? So all of our y values this time are above the value of 2, so we're only going to go from 2 to positive infinity for our range this time. Any questions about that? Okay. Now, if you weren't 100% sure about, say, the vertical asymptote here, right? So just looking at that graph, maybe it's hard to tell, is it actually approaching x equals 1? Is there another way we could have found that vertical asymptote instead? Okay, and what are we going to factor? Good. So we know the denominator can't be equal to 0, right? So we could have taken this denominator, x squared minus 2x plus 1, and say, well, we know that cannot be equal to 0. And now we could factor this and see what x values we would get, and that should tell us where we have a vertical asymptote. So if I were to factor this, this would give me x and x. The factors of 1 are 1 and 1. And in this case, we need a negative 2x, and this needs to be positive, so it's going to have to be a minus and a minus. And so now if we set each of our factors not equal to 0, they're the same factor, right? So x minus 1 can't be equal to 0, and then moving the 1 over gives us x cannot be equal to positive 1. And so that's what tells us now that we have a vertical asymptote at x equals 1. So we could do this algebraically even without looking at the graph to find that vertical asymptote. So just so you know, right, on a test, this is kind of what I'm going to be expecting to see in terms of work for these, right? When you're asked to find a domain or find your vertical asymptotes, is actually knowing to take the denominator, say that it cannot be equal to 0, factor necessary, right, and then actually find those values that are your restrictions. Any questions on that one now? Okay, if it can't factor, you could technically use quadratic formula. I'm not going to give you anything that would be that complicated just in terms of time, right? But technically, if this thing did not factor, you could use quadratic formula on it, and that would actually give you the vertical asymptotes also. They would just be irrational values instead. It is, right? So Naomi, you were asking, is that the restriction? So that x is not equal to 1, that's your restriction. And so that's why our domain had a restriction positive 1 there. Yes, Sarah.
Is there, I may have missed this, but is there a way to find the horizontal asymptote algebraically?
I am glad you asked, because that's the very next slide. Okay, so that's where we're headed right now. So any other questions on this one? And then I'll pull that slide up. All right, good there. So here's how we can find horizontal asymptotes without actually having to look at the graph. Okay, so we're letting this rational function look like this, right? So you don't get bogged down in the notation. Oops. There we go. All right, so we've got a polynomial in the numerator. We've got a polynomial in the denominator, right? That's all we have here. If we're looking for vertical asymptotes, we know we just want to figure out where's the denominator 0, right? Okay, so we talked about that. We set the denominator not equal to 0. We factor if necessary. We find those values, and that'll actually give us the vertical asymptotes. If we're looking for horizontal now, what we're going to be looking at are the n and m values from up here, meaning we're looking at the degree, right? So we need to look at the degree of the numerator. We need to look at the degree of the denominator. If the degree in the numerator is less than the degree in the denominator, so if it's smaller than what's on the bottom, then we're always going to have a horizontal asymptote of y equals 0. Okay, so there's no other work to be done there. If the degree in the numerator is smaller than the degree in the denominator, always y equals 0. If the degree in the numerator is equal to the degree in the denominator, then we're going to divide the coefficients here. So the a sub n and the b sub m, that's just the numbers out front. We can divide those, and that will give us our horizontal asymptote. If the degree in the numerator is bigger than the degree in the denominator, then we don't have a horizontal asymptote at all. Okay, so those are the three cases, right? And so that's what we have to look at, is just compare your degrees on top and bottom, and then follow these rules. Smaller on top than the bottom, y equals 0. Equal degrees, divide the coefficients. If the top is bigger than the bottom, then there is no horizontal asymptote at all. So I'll give you a minute to write that down, because I think that is something you might actually want to have in your notes, just to remember what those rules are. And then we'll see if we have time for an example. We might have to hold off on that one until next week. But I can at least kind of give you an idea. I want to at least look at the example to show you what I mean by this in terms of actual numbers. All right. If I need to bring this back up, I can at the end, okay? But for the last couple of minutes, I do want to look at the next example, just so we can actually see what I mean in terms of actual numbers now. So go ahead and write down this function here, and then we're going to see if we can find the horizontal asymptotes just based off of those rules that we just looked at. Okay, so like I said, for the vertical asymptotes, we're just going to set this not equal to 0. We're going to factor if possible. We're going to find those. Okay, so I'm not going to take any time to do that right now. We'll spend some more time doing that next week. I want to focus on the rules for horizontal asymptotes right now. So horizontal asymptotes. First thing we want to do is we're going to look at the degree in the numerator and the denominator. In this case, I have an x squared and an x squared. Well, since they're both squared, that means my degrees are equal to each other. So if that's the case, what are we going to have to do to find the horizontal asymptote this time? Divide, right? And specifically, we're going to divide what values? Three over 2. Good. So our horizontal asymptote this time is just y equals 3 halves. Okay? And that's all there is to it. Okay, so it's just a matter of figuring out which case do you have, right? Because because there's 3 options. In this case, this is where the degrees are equal to each other. So all I'm going to do is just divide those 2 numbers, and there's my horizontal asymptote for that one. And you can always double check by graphing, right? So always keep that in mind. You have access to the graph. Look at the graph, make sure it matches what you got here. Any questions there now? So I will put back up the last slide just in case anybody did want more time to get those rules down. But that's where we'll stop for today. If you have any questions, feel free to hang out. I can stay around for another 5 minutes or so before I have to get set up for my next class. But thanks for coming. Have a good weekend, and let me know if you've got questions, as you're working on homework or anything, or if you need to set up a meeting with me or anything, we can always do that too. Okay, so have a good one. I'll see you guys Monday. So I think right now the homework is set to be due on Monday. That's going to get pushed back because I need a couple more days to finish. So I'm guessing probably middle of next week, probably Wednesday is when that should be due now, Kenneth. Could you also find the inverse of the original function, find the restriction, which gives the range? You could. So yeah, German's question is, could you find the inverse and then use the domain of the inverse to know the range of the original? And remember, that's something we did earlier, so technically, yes. I don't know that it's really worth it, just because in a lot of these cases, it's going to be easier just to find those horizontal asymptotes, right, using our 3 rules, than it would be to actually go through that whole process finding the inverse, okay? So yes, it's legitimate, right? It's good math. I just don't know if it's worth the time and effort to actually have to do that. That's all. Any other questions? All right, so I am still here for a couple more minutes if you got any questions, and I'll leave this up here, and I will see you guys next week.